We are now on problem solving exposed. Okay, now I've got various problems which I am intending to take you through to solve and illustrate this problem solving exposed method. Okay, the idea is that by the end of this method, along with the ninja question analysis, you ought to be able to solve anything. Obviously, some problems are more difficult than others, and exactly what route your thinking goes down will make a difference as to how easy it is for you to solve your problem. So, hopefully, this will help you. Okay, now I wanted to make sure that none of you had seen this question before. It looks horrific and it takes a lot of thinking about, which is one of the reasons why I chose this. You can have access to this paper. It's from 2008, I think. And the mark scheme for it afterwards. I'll let you have it afterwards. But without looking at the mark scheme, because that's what you will be doing in the real exam, I want you to do the ninja question reading thing on this. Okay, so if we start with our ninja question reading, that is the first step in problem solving exposed. Okay, so we are going to figure out what this question is about. Okay, so can anybody look at this question, have just a quick look at it? We've got to show that. There's my command word. Okay, let me do yellow. There's my command word. It's show that. I've got a calculate and another calculate. So we've got to show that, and we're showing about a speed. So it's basically calculate what speed is. What topic is this? Can anybody tell me? Newton's laws, yeah, I'd go with that. Well done, Kayla. Newton's laws. Okay, so Newton's laws, it's mechanics, isn't it? Okay, right. Next bit of our ninja question reading. Okay, we're going to highlight. Oh, we should go away and find our open your data sheet. In fact, you should have one right next to you right now. Open it up at the mechanics bit. The next thing that we're going to do is we are going to highlight all the numbers. Okay, highlight all the numbers. Oh, we've got a depth, we've got a width, we've got a mass. We've got the words every second. Oh, that's important. Okay, we've got negligible kinetic energy. That means that that's 0. What else have we got? We've got the density of the gravel. I think right down here we've got negligible friction. Okay, and we've got the word every second there. Okay, I think that might be it. Can anybody see anything else? I think I might have highlighted all my numbers. Okay, so in my ninja question reading, what do I then do? Well, then I need to read for meaning. And I need to draw a situation of what's going on. Well, we've got a picture of what's going on. Okay, I am going to draw something though, because I want to make something a little bit clearer to you. And drawing this when you read through actually will help you solve this problem. Okay, so we've got figure 4. Okay, it says it shows a conveyor belt and it's moving gravel horizontally in a quarry, and you can see that it's coming down quite fast and it's forming a layer, and they've told you the thickness of the layer. Right, now I'm going to draw a sort of 3-dimensional view of this. Okay, so there is my layer. I know it wouldn't have sharp edges, but there is my layer. of gravel on my conveyor. Okay, and I've drawn it as if it ends because that much moves past my hopper thing in 1 second. Okay, so that's D, but my velocity, which is what I'm going to try and work out, is equal to D over T, and that's 1 second. Okay, so now can you begin to think about what's going on? Right, okay, so, and it's moving to the right. Let's draw a lovely arrow on it. Okay, it's negligible initial kinetic energy, so it's falling and it's basically stationary when it's falling. Then it says the gravel has an average depth of, and we've got a depth information. Okay, let's add these numbers. 0.1, oh dear, can't see that. 1 meters, so 11 centimeters, and the belt is 0.76, so this distance is 0.76 meters. Okay, and we've got 48 kilograms every second. So the mass of all of this, right, the mass is equal to 48 kilograms. Okay, and Ray has put something in the chat which says D is equal to M over V, where V is the volume, volume, and velocity, volume is velocity times width. We need the depth as well. Bit confusing because there's too many V's. V for volume, V for velocity, too many V's. We've got to be really careful with this. Right, okay. Okay, so we've got, there's our mass that's falling, and that's the mass of the volume of that, which is passing this point every second. And so we, yeah, D over T, that's what we want. We want the velocity. Okay. Right, now it says show that the belt moves at a speed of about that. So that's our velocity that we want to figure out. And then there's this enormous clue, which is the density. They've given you the density. What's the density equation? It's mass over volume. Okay, mass over volume. Okay, and when you've drawn out your volume like I just did as a three-dimensional cuboid, we can then say, oh, hang on a minute. We've got mass over, and it's the D, which is our distance sideways, times the, I'm going to call it H for the height, and I'm going to call it W for the width. Okay. And I actually want D over T. So what I'm going to do is I'm going to put D up, okay, and have it on its own. So make D the subject. So this whole equation becomes M over H times W. And then we also have to multiply it by our density. That's just exactly the same equation, but rearranged. Right, now, we don't want D. We want D over T. Over T over T. If I just put it in there, it's divided by, right, now I want you to realize that my mass isn't just 48 kilograms, it's 48 kilograms every second. Ba, ba, ba. So this M is our mass per second. So there is my second bit. Can you see that 48 kilograms is actually M over T? That's what we've got. So we can get D over T. Oh. Ooh, okay. So all we've got to do is think of it as a cuboid moving past a point. And we've got to deconstruct our volume. Oh my word. Okay. Can you see how difficult the conceptual thinking is here? This is a flow, if you like. And whenever you've got things changing with time or things happening in a second, it makes it more difficult to think about. Okay, so now this is the equation. That's what we want. Okay, so and we've got m over t. Okay, that's what we were given. We weren't given m, we were given m over t because it's the rate. It's 48 kilograms every second. Can you see why it's important that you highlight that word? Okay, so in fact what we've got to do is we're going to that's v for velocity. This is m over t. Yeah, this is m over t. Let's do that like that. And then we've got the height and the width and the density as well. And that will give us the right answer. Right, now, that is difficult. And I, years of teaching has said to me, right, well, how can I mechanize that thinking process that allows you to pull together all those clues that will allow you to solve a problem like this the next time you come across a problem like this, okay? How did you know that you could model it as a cuboid? So how did I know? Well, experience, but plus they told me, because they gave me the depth, they gave me the width. Why would they give me those things if they didn't want me to use them? Nearly never do they give you information in a question that you're not going to use. It's really quite rare, very occasionally in multiple choice questions to kind of put you off. And if you've got a whole table of data and they're wanting you to pick out the relevant bit, then they might not. They might give you information that you don't need. But most of the time, the only information they give you in a question is stuff that you're going to need. So, and that's what I mean about we need to mechanize this thinking process that lets us come up with a way to get to an answer. Okay, and so for this question, I wanted to go through the method. So on your sheet, don't know if you can see in the picture, on your sheet where it says problem solving exposed at 10 o'clock, this is what I want you to write down, okay? So the very first thing I want you to write down is, number one, what do you need to find? Okay, I've run out of room, so I am, and what am I going to do? Do you know what? I think I'm going to do this as a whiteboard. Okay, so this is problem solving. And this is a method which hopefully will at least help you, if not absolutely solve every problem for you. Okay, so this is a method. So the first thing is you've got to figure out what is it they want you to find. What do they want you to find? Okay, and in the example that we had, it was V, which was D over T, wasn't it? Okay, so that was in the example. Okay, so then the next thing, after you've figured out what it is they want you to find, the next thing is to ask yourself questions about what is required to find that answer. Okay, so ask yourself questions about, oh dear, I can't write today. What is required to find that answer? And in physics, we're looking at what equations. Now, do you remember that we had the density? That was a big clue. Okay, and the volume is also an equation. Remember, it was the distance travelled sideways times the width times the height. Okay, now those two were what was needed to kind of construct D. But where was the T coming in? Where was the T coming in? Okay, now the next bit was that I want you to do is I want you to look for clues in what you've been given. So this comes back to Arian's comment, which was, how did I know that we can model it as a cuboid? And we were given the clues that told me that, because here we had the width and we had the height, okay, of the material, the concrete stuff on the conveyor of material on the conveyor. How do you spell it? Conveyor, is that right? So those were the clues. Those were the clues. So remember that you do need to combine this with your Ninja question analysis. So you're going to notice those numbers, those things you've been given, the symbols, the relationships. You are going to notice them because you are practicing using your Ninja question reading, your Ninja question analysis. So you're looking for those things. And you're going to ask yourself questions. Well, what do I need to get D over T? How can I get D? How can I get T? What is the clues? What are my relationships that I've got? What information have they given me? Right? So, so the next thing is, so look for clues in what you've been given. And in fact, do you know what? Can I add in this extra little bit, which is draw the diagram. Okay, and I want you to use your clues. Because in this case, it was a mechanics question. It's about something moving. It's about things, you know, traveling. And they want to know a speed. And it was like, well, the picture that they gave us was like, it was only 2D. And okay, so use your clues. Okay, so we were given the width and we were, right? So there was an extra information. In my case, I drew a three-dimensional diagram. Okay, so let's add that in. Okay, so I'm going to add in a 3D diagram. Okay, it might be, if it was an electrical experiment, it might be redraw the diagram with an equivalent circuit. So you've now worked out what your parallel resistance comes to, and you can replace it with a single resistor, and or you've added in your internal resistance. So you can include that in your calculations or whatever it is. So draw a diagram, redraw the situation, figure out, especially if things are changing with time, what the situation is before and after. I mean, this is absolutely routine for a momentum question. Momentum situation before, momentum situation afterwards. And so you need to use this information to help you figure out what's going on, to help you think about it. Okay, and then the next thing is you need to try multiple equations. Okay, multiple equations. I mean, usually you won't have to apply all of these rules. If it's a dead simple, you know, calculate this, E is HF or something, it's straightforward. It's like you go, yay, I get 3 marks in my exam. It's just mechanical. You just plug your numbers in. But if it's more than one equation, and it nearly always is at least 2, you need to try multiple equations. You need to substitute in. So, okay, so this is the substitution. you know, from one equation into another equation, okay? So here we substituted in the equation for density into the equation for velocity, okay? And we substituted in the equation for volume into the equation for density. Can you see it's 3 equations, isn't it? Okay, so that's so multiple equations and substitution. You've got to kind of work your way. This is why it's easy to start at the end, so you figure out what you want to find first. That's your end point, that's your goal. You've got to figure out which way you're going to, you know, the grandma's house. There's your Little Red Riding Hood, and you've got to avoid the trees. Okay, so you've got your information which tells you which route. Those are the equations that you've got, and you're looking for clues in the question. Okay, drawing a diagram, that's your map. Okay, and then trying multiple equations, substituting from one equation into another equation to link these ideas. All right, okay. Having got to that point, then you need to then, in this question, and this is often the thing that makes a question almost impossible to do, you need to think about rate, okay, when things are changing with time. Okay, so think about rate, and quite often you can just divide by t. Okay, here by t. I'll get rid of those lines. I guess people didn't mean to do that. Okay, so so think about rate. In this case, you can just divide by t, or you can think, think what happens in 1 second. So there's a big clue, which was each second, that phrase. Okay, that's a huge clue. Okay, that there's a rate thing going on and that you need to allow for that. Okay, now the places, I mean, obviously with speeds and distances and times, right, rate is important. If it's a power question, so quite often in electrical questions you get electrical power, that is energy per second, so that brings in the time. Current is charge per second, that brings in the time. You've got obviously speeds, momentum, because of this v, the velocity and the momentum, that is per second as well. Okay, be aware of this. Okay, and make sure that you are thinking about rate. If you can't do something, it might be that it's rate. If you've just got energy, like in the photon question before, and they wanted to know photons arriving per second, oh, suddenly it's energy per second. Oh, now I'm thinking power. Okay, so these are the steps. Now, this is not absolutely guaranteed to get you to your answer, and obviously you still need to use all of you have got massive brains. I promise you, you are the cream of the crop. You are some of the most intelligent 17-18-year-olds in the country. Those are the people that do A-level physics. So honestly, truly, you can do this. It's something that gets easier with practice. So we need to practice using these skills. Okay, that's what we need to do. Okay, right, so the next thing we're going to do, we've got a few minutes, about 25 minutes. We're going to practice using these skills on a question. Okay, so I'm hoping that you've written this down. This whiteboard will appear in the chat, and I will add it to the course at the end of the day. So if you want to give yourself the problem solving method that I just wrote down. It is in the chat right now. There's a link to it. You can open it and save it somewhere for yourself. Okay, right now I'm going to go back to my question. Okay, so we've done 3 part A, right? And now what I want to do, is I want to look at 3 part A, I. Again, we're going to use our Ninja question reading, and now we're also going to use our problem solving method to see if we can figure out what to do with 3AII. Okay, it's calculate, and we've got to calculate the force. Okay, we already know what the situation is. We've got concrete or something, gravel. And it's moving along a conveyor, and we've worked out how fast it's going, or if we couldn't, they've given us how fast it's going. We're probably going to need that because this is a show that question. So we need to use the speed of the conveyor, which is 0.3. And I think it works out to be, if we do the sum, it works out to be 0.32 meters per second. I didn't actually do the sum, but you can do it. Right, now, we've got a speed. We've got a speed. And what have they asked us to work out? They've asked us to calculate the force. Okay, remembering in our problem solving method, what do they want us to find? They want us to find the force. This is a mechanics question. We've already done our Ninja question reading. What are the mechanics forces on your data sheet? Okay, well, it might be MA, it might be delta MV over delta T. Maybe you've got this one, which is impulse and momentum. Okay, so right, any others? Force. We've got the work is force times distance thing. What else have we got? We've got a power equation, haven't we, which has got force in it. That's got velocity in it. Ooh, I wonder if that's going to be useful. I can't think of anything else off the top of my head. If you've got the data sheet in front of you, maybe you can spot some other things. Right. Now, it says, calculate the force required to keep the belt moving steadily. Forces aren't required to keep things moving steadily unless there's friction. And in fact, later on, they tell you there isn't any friction. So what on earth is the force used for? What are we accelerating? Because you need to be accelerating something in order to need a force. You know, acceleration is not zero if F is not zero. So we're accelerating something. Okay, what are we accelerating? What are we accelerating? Okay, so we've got using A is V over T. Okay, so we've got A. Kayla has written A is V over T. I'm going to write delta V over T. Okay, which is it's V minus U over T. That is A, that's the standard, that's the V equals U plus AT in our SUVAT equations. Okay, Kayla's written, using A is V over T, acceleration during the first second is 0.32. So we can do F equals MA. Good. Okay, so Michaela has cracked it. She's like, well, hang on a minute. The thing that we're accelerating is this gravel that's arriving with zero velocity. We know it's got zero velocity because it has negligible kinetic energy. Okay, so it's arriving with zero velocity and it's got to go at the speed of the belt. So some force has got to be accelerating it. Yay! Can you see? the thinking. That means that we've got, right now, that means that we can work out the acceleration because we've got V. Oh, look, we needed V. Why did they tell us V? Yes, we're cooking with gas. We can you see? All the clues are coming together, like Sherlock Holmes. The clues are coming together. Right, okay, so we're going to go 0.32. Our initial velocity for our gravel is 0, at least sideways it certainly is, divided by, 1 second, one. We're going to go with 1, where this is each second. Okay, and there's our acceleration. Ha ha ha. Right, okay, so now we can do F equals ma. F equals ma. Okay. Right, so can you see that the m it's the mass each second? Oh, it works out beautifully. We've got our acceleration for each second, or mass for each second. Yes. Okay, so this becomes 48 times 0.32. Can you see how simple it is? Can you see how difficult the thinking was? The thinking is really hard here because it's not obvious that you need a force at all. Okay, that is problem solving exposed, right? So we did it. I mean, it's really simple actually, but the thinking required is hard. That's the big bit that's missing from most walkthroughs. It's the thinking you've got to do to get to your answer, right? What have I got to do? Well, in the walkthrough, they tell you, but why have I got to do that? How can I get to that answer on my own, right? Okay, so the next thing then is we are going to move on to part I. So let me just move this little lot up. We're going to do part I. Let's get rid of these twiddly bits. Right, okay, so now it says calculate the force. Oh no, we've done that bit. Part 3, I. The steel rollers are driven by an electric motor. Okay, it says assume, right, we're back to our ninja question reading. There's negligible friction. And they want us to calculate, there's our word, and it's the energy delivered, but it's every second. It's power. Energy every second is power. So we need power. That's what we need. We need power. That's what we're looking for, power. Okay, and this is part I of a 3-part question. Okay, so what have we just worked out? We've worked out force. Do you think we might need that in the next bit? Is there a power equation that has force in it? Can you see the thinking? Yes, well done, Abia. So P is FV. There it is. It's one of the ones I wrote down. One of the ones that should be in front of you on your data sheet because you've opened it. And you can just look and go, oh, look, there's the power equation I need. Okay, so we just plug the force in that we got from here. So this, we didn't work it out. 48 times 0.32. That's my force. Can you see? Right, and then I'm going to multiply that by my velocity, which is this one. Okay, 0.32 again. Okay, and that is this, of course, is every second. Yes. So, yeah, there we go. So that one's easy, dead easy, much easier than you think, because of the hard thinking that you did in the first 2 parts. Right, now, let's move on. This is part B. I'm going to get rid of all my drawings because part B is going to be less closely related. Okay, but again, can you see? Let me change colour. Can you see, though, that we've got another show that? Okay, we've got to do another show that. We've got to show that the total kinetic energy gained every second is about 2.5 joules. The total kinetic energy gained every second. about 2.5 joules. So this question, well, what's it about? Do you think it might be energy? Do you think it might be kinetic energy? What's the kinetic energy equation? Half mv squared. But it's every second, so actually it's power. Okay, so it's over t equals power. Okay. Okay, so but we've got, it's the change in kinetic energy. Can you see that word there? And it's only the horizontal motion that they're worried about. So we're going from 0 meters per second, and we're going up to 0.32 meters per second because of the previous question. So so we can work out that our initial kinetic energy is 0, so we're subtracting 0. So the change in kinetic energy then is it's a half times the mass. Well, that was 48 kilograms, wasn't it, each second? This is now over time, because that one's over 1 second. Can you see it's over time? Yep. Times, and then it's 0.32 squared. So there is my kinetic energy, and that should be 2.5. When you actually do it, you get 2.46 joules per second. It actually works out as 2.16 if you use the 0.3, which was the original show that speed thing. Okay, but that's nearly 2.5 joules, which we've confirmed. But the fact that we have a show that means that we're going to be using that in the next bit. That's definitely going in the next bit. Okay, so comment on the difference between the two energies calculated in part A, I, and part B, I. Okay, so there is part B, I. The part A, I. Did I work it out? Did anybody actually work it out? I didn't work it out. I didn't work it out. The difference is due to the need to accelerate the gravel, basically. Somebody wrote down it was 4.9. Thank you very much, people. So it's so I we got 4.9 watts, and BI we got 2.5 watts, and the difference is the energy needed to accelerate the gravel. Okay, so energy needed to accelerate the gravel. Okay, and where does it end up? It ends up in as heat. Usually, I mean, it's always heat in the gravel and belts. Yeah, heat. Internal energy, if you prefer that. Thermal energy works too. You need to say where it ends up. Okay. It's not clear that you need to say where it ends up. So again, this is again, we'll do it when we do command words, but this is the difference between comment and it doesn't tell you everything. You're expected to kind of figure out what it is you're expected to say. This is comment, so there is a difference. The difference goes to accelerate the gravel. That would be explain. Can you see? Okay, that's an explain answer. But comment, it's comment. So if you've got a difference in energies, where's that difference going? It kind of follows, but you do need to say if you want to get all the marks here. Right. Okay, let's move on. The conveyor belt is made from rubber. Right, now this sort of question requires knowledge. So this is the sort of thing that you can only get from learning the physics. Okay, steel wires, very strong, nice and straight, big stress, little strain. Okay, rubber, It's not a straight line. Okay, that's what rubber would do. Let's do it again. Something like that. And it goes back down a different line. It goes back down that way. But they only want the one on the way up, so let's get rid of it. Got rid of all of it. Right now, I want you to realise that this is the rubber, and this is the steel. Steel has a much bigger breaking stress than the rubber, so it's further up. It's harder to stretch, so gradient is bigger. That's the Young's modulus, and the steel wire is straight. Well, until it starts plastic deformation. But the rubber is a curve. It is elastic because when it goes back down to its original length, but energy is stored in the rubber. It gets hot if you stretch, and I don't know if you've ever done it. But anyway, so the big difference is that the rubber is curvy, the steel one is straight, and it won't tell you this on the mark scheme. The mark scheme says correct shaped curves. So, yeah, they're expecting the person that's marking it to know what it looks like. Okay, right, okay. Next one then. Let us try, I mean, the next bit is relatively straightforward. This is, and perhaps I should do it for the year 12s. Okay, so this next one is, they've just given you a load of information. There is nothing hard about this at all. The thinking that you have to do is not particularly difficult. You've been given a huge clue that it's Young's modulus. So you've got your Young's modulus, which is E. I don't know why. Why can't they use a capital Y? It's almost not used at all. But anyway, E, it's stress over strain, and stress is force over area, and strain is change in length over the original length. They want you to calculate the extension. So delta L, make it the subject of the equation. And then you just plug your numbers in. You've got your force there. You've got your original length, 78 meters. You've got your area you can work out from your thickness of your belt and your width of your belt. They've given you Young's modulus. Giga means times 10 to the 9. Just plug your numbers in and you get the extension. Nothing particularly difficult about that. The 6 marks is not just for that bit. This was a WJEC paper. No, it's not. No, it's not. I lie. This is an AQA, but like I say, it was from 2008. So can you see, there's the previous 6 marks. So the 6 marks are for, can you see that's 4? So it's for part C. So you've got probably 3 marks there and probably 3 marks there without looking at the mark scheme. I have pulled up the mark scheme actually. Shall I pull up the mark scheme? Yeah, so here's the mark scheme. So we've got correct shape for rubber, correct shape for steel. The stress calculated, they want the strain calculated. Then you can get your delta L. There is, and then it says appreciation that the answer must be to 2 significant figures, 2 or 3. So you need to get your significant figures right for WJC. Sorry, for in the olden days, use 3. You routinely use 3 unless there's a really good reason not to. Use 3 significant figures in your answers. Right. Okay. So that was that question. Right. How long have we got? We've got just 5 minutes before I need to go on and start to teach year 12 their content topics for today. What I'd like to do is let's just have a little look at this question. So we've got the first bit, it was 4B, right? So this tells you that it's about wave particle duality, and then it goes on to talk about the photoelectric effect. This is a 6 mark question. We are going to do a whole session on 6 mark questions, so I don't want to cover that one now. But I want you to spend the last 5 minutes looking at question 4. There again, this question conceptually quite hard. Okay, so I'll just let you read it. Do your ninja question thing in your head. Figure out where the numbers are, etc., etc., etc. Okay, I'm gonna do it, and then let's see if we can solve this problem. Now, the diagram that I've drawn is designed to help you think about this. Remembering our problem solving exposed method, what do we need to find? We have got to find the time. Time, that's what we've got to find. Okay, so this is a rate thing. We've got to find the time. What the next thing is, what questions? Okay, what is it that will what equations relate to this? What's going to give us our answer here? And they've given us the work function. Okay, so that is the energy necessary to lift an electron from where it is in an atom to the surface so that it can leave. Okay, so that conceptually, that's the energy that needs to be given to the electron. That's it. That's what we're trying to find, because it's the time taken to absorb that much energy. Okay, time taken to get electron. Okay, 5.9 times 10 to the minus 19 joules of energy. Okay, right, now time then and energy together give us power. Okay, and what have they given us? They've given us the energy delivered by the lamp per second. That's what's for each square meter. That's actually intensity. Intensity is power divided by area. Not on every data sheet. Intensity is power divided by, mostly it's for stars, and it's 4 pi r squared, where that is the surface area of the sphere that the energy is being spread over. So some data sheets have got that. Some data sheets, instead of the word power or a symbol for power, they've got a capital L for luminosity. Luminosity is measured in watts. It's the power of a star. But there is, so what this thing, each square meter per second, that is giving us the intensity. But they've given it in such a way that they've given you the energy. It's the energy arriving on this entire area every second. Right, now, the energy arriving on that area which is the energy that can be absorbed by one electron, okay, is going to be that fraction of the total area. Can you see the thinking you've got to go through here? This is hard. Okay, so we've got the area of the atom, that's the energy that's absorbed by one electron, divided by the 1 meter square area, and that fraction is the fraction of this much energy that we're going to get, 0.023. That is the energy given to an electron, and this is per second. Okay, that's what's happening, energy given to an electron per second. So if we've now got the energy in 1 second, and we know the energy, the total energy that's required, we can do our number equation to find out the number of seconds. Number equation again. Okay, so the number of seconds is going to be the total energy required. So that is the work function divided by the amount of energy coming in 1 second. So the energy per second. Can you see? This is a hard question. So there is my energy per second. So it's the area of my atom. Multiplied by the 0.023. That goes in there. And then the energy for the work function is this. And that will give us the number of seconds. Isn't it horrible? It's really horrible. Right. Hopefully you can now have a better bash at answering problems, proper problems. These ones that I've shown you today. This is AQA Physics B from 2008. Okay, so this is proper physics. It hasn't changed, people. The questions were always hard. Okay, hasn't got more hard. They're pretty much the same. So, but you can see it's not simple thinking. You've got now, I hope, your problem solving method, which will let you solve any problems like this.